what we almost finished yesterday. um, the next scenario is if the density function is uniform or is constant. Then now we're going to be talking about, instead of a center of mass, a centroid, which is located pretty much based off of the figure or the shape or the whatever you have, and is exactly where it should be, because it's not weighted differently at different points. So if that's the case, if we just take a look at our formulas, the x-coordinate for the center of mass was 1 over mass times the double integral of x times the density function, dA. But now, if we rewrite things, and just replace mass with the formula for mass, which is exactly the same as the numerator with the exception of the x. Whoops, forgot my region R. The fact that the density function would be constant means that these would what? These would cancel out. So then what you're left with is the double integral of region R of x dA over the double integral over region R of 1 dA. And we have a name for this. What does this tell you? It tells you the area of the region. So if I rewrite the formula, this is the same as 1 over the area of R instead of the mass times the double integral of x dA. So this would be the x-coordinate. And similarly, the y-coordinate would be the same. Just integrate y instead of x. So easy to remember. So let's do an example.
So you use the same symbol for centroid and center of mass?
Yes, because it's just the central locate. I mean, it just depends on the context. So I mean, if you want to be more specific and you want to write a subscript and write CENT or whatever, that's fine. But so let's say our region R looks something like this. So this is R. Do we know one of the coordinates already?
0.
For which one?
Y.
If y is 0, that means the centroid is on the x-axis.
Or, wait, no, it's in the middle of the thing. Yeah.
So it's on the y-axis, which is where x is 0, right? So this is obvious. You don't have to do any calculus to figure that out. The reason is because this is uniform density, so it's not going to be weighted on one side versus the other. It's going to be right in the middle. Now, where along the y-axis it's going to be is going to depend on the calculation. So if we set up the calculation, we do 1 over the area, but this is a circle, so I don't even have to do the double integral because we can find the area of a half circle, right? Half pi, what's the radius here? A, so pi a squared. Now, if we didn't have such a nice shape, then yes, you're going to have to do a double integral to figure out the area of R. What's that?
I thought your squared was an equal sign for a second.
Oh, no, sorry, that's, yeah. Okay, so then now all we need in here is y, dA. And now we just make a decision as to proceed with rectangular coordinates, or maybe what?
Polar.
Polar's probably easier, right? In polar, y is,
R sine
and then dA would be
theta. R
good. And now our bounds would be for r from 0 to a. Theta would be from 0 to pi. Good. Let me just write this as 2 over pi a squared. R squared becomes 1/3 r cubed sine theta, evaluated from r equals 0 to r equals a. Am I still on the screen? No. So then that's 2 over pi a squared. Plug in the bounds, we just get integral of 0 to pi of 1/3 a cubed sine theta d theta. So then that would become negative 1/3 a cubed cosine theta, and that's from theta equals 0 to pi. And if you plug in the bounds, when you do pi, that's negative 1 times next, so that'll be positive 2a cubed over 3 pi a squared minus, now we plug in 0, that's going to be positive 1 times, so that'll be negative 2a cubed over 3 pi a squared, for a grand total of 4a cubed, but then the a cubed and the a squared, obviously you can simplify that, so you just get 4a over 3 pi. Okay? So that would be the y-coordinate, and the x-coordinate was 0. Okay? So all that's left to say is a couple things. We're done with learning material for the unit, but just a couple of tips. First of all of these extend to 3 dimensions also. Oh, thank you. Excuse me. So all the formulas we did extend to 3 dimensions. So mass, let me make it lowercase. So if we have a 3-dimensional solid with a certain density function, now the density function would be in terms of 3 variables, and we'd integrate over the solid g with respect to dv. And then the center of gravity, or the center of mass, formulas would be similar. So it would be 1 over mass, but then now we have a triple integral of x times the density function dv, and so on. Obviously with y it's the same thing, just y in the integrand. With z it's the same thing except z in the integrand. And now when the density is constant, it's the same idea. So for the centroid, x bar would be not 1 over area, but now it becomes what? 1 over volume times the triple integral of, if we're looking for x, it'd be x dv, and so on and so forth. So all these formulas extend to 3 dimensions, depending on if you have a surface, a flat surface, or if you have a solid.